Hey guys, thanks for tuning into our video. My name is Adam, and with the help of Nick and Manny, we'll be talking to you guys a little bit today about turbo machines. A turbo machine is a mechanical device that operates to either add or extract energy from a fluid. There are two broad classes, and those are pumps and turbines. In pumps, work is done on a fluid to increase the energy of that fluid, whereas in turbines, fluid does work on the turbine, and this lowers the energy of the fluid. Both pumps and turbines come in a wide variety of configurations and have different applications in everyday life and in industry. There are three key physical characteristics that both pumps and turbines share in common that are critical to their functioning. The first are the blades, which receive and direct inlet airflow through the flow passage. The blades are attached to a rotating portion known as the rotor, which rotates upon a central axis, also known as the shaft. Pumps and turbines can be broken down into three categories based on how the fluid moves through the flow passage. If the fluid moves through the flow passage in an axial manner, you have an axial flow turbo machine. If it goes through in a radial manner, you have a radial flow turbo machine. And if it's some combination of the two, you have a mixed flow turbo machine. To better understand how turbo machines work, it's important to be able to quantify some of their functions. Here we're going to focus on three variables: the blade speed U, the absolute fluid velocity V, and the relative velocity W. We can combine these vector components into the equation V equals U plus W. With some simplifying assumptions and the help of Newton's third law, we can use this equation to construct velocity diagrams like those shown here. Provided here are some common equations that you're likely to see in dealing with turbo machines. We start with the moment-to-moment equation, where the left-hand side is the sum of the external torques acting on the contents of the control volume, and the right-hand side is the net rate of flow of angular momentum through the control surface. For a 1D steady flow approximation, we arrive at the Euler turbo machine equation, which defines shaft torque. Using a few simple relations, we arrive at equation 6, the work per unit mass of a flowing fluid, which is in terms of the variables U and V we specified on the previous slide. There's also an alternative definition, which has the terms U, V, and W. And this conceptually shows that the work is associated with the change in kinetic energy, centrifugal force, and the reaction to acceleration or diffusion of flow in the blade passage. We can also see from this that the most effective pump will have a kinetic energy increase, flow radially outward, and have a negative acceleration within the blade passage, whereas the most effective turbine will have a kinetic energy decrease, flow radially inward, and have positive acceleration within the blade passages. From here, I'm going to pass it off to Nick, who's going to talk a little bit more about pumps.
Alright, now we're going to be going over pumps. In general, pump structure is made up of an impeller with a casing. The impeller is a series of blades that rotate around the eye, the center right here. And the casing goes around the impeller, and its shape, specifically that it increases in area as it goes towards the discharge, will reduce fluid velocity and increase pressure. So the impeller sucks in fluid on one side, so you have an inflow over here. It'll go through these propellers out the eye and across through the impeller. Some common types of impellers, these blades, are open, where the blades are exposed on one side, double suction, where the fluid enters on both sides, and multi-stage, where there's several impellers in the series. And this can be useful if you want to create a very high discharge at the very end. So head, or the discharge pressure, can be approximated with the difference of pressure over gamma, where gamma is the specific weight of the fluid. And we can also define the overall efficiency of the pump with the power gained by the fluid over the shaft power driving the pump, defined by these variables here. And the efficiency will be lowered by things like the hydraulic losses in the pump, mechanical losses, which is stuff like friction, and power losses from leakage in case the pump isn't sealed properly. And we can say that this is also a function of all three of these things. We also have rising head curves for decreasing flow rate, though it doesn't quite show it on this graph, it might show it in others. falling head curves will initially rise as Q decreases, but will fall eventually as Q continues to decrease. Then we have NPSHR, which is another way of defining a pump. It's the net positive suction head. It is the minimum suction to keep vapor bubbles from forming in the pump. Because if you can imagine, if you have low pressure relative on one side of the pump, you might end up with the fluid basically vaporizing. And this is often found experimentally, hence the R. Now some system characteristics for a pump. For a typical flow system, we can obtain a system equation of this form, where the K depends on the pipe sizes or lengths, the friction, or any other minor losses that we can account for. We can find the operating point of a pump from the intersection between the system equation and the performance curve. So see here we have a system curve, and these two black lines are the performance curves, and these intersections A and B are the optimal operating points of these pumps. Now for pumps in series and parallel, these might be useful in case you want to increase flow or head capacity, but just having two pumps is not going to double either of those parameters. If you have them in series, the pump performance curve is going to be the sum of the heads at the same flow rate, as shown in A over here. Or if you have pumps at parallel, the pump performance curve is the sum of the flow rates at the same head, as shown here. Another way to define pumps, or relate pumps rather, is pump scaling laws. These are dimensionless variables used for comparing geometrically similar pumps, which basically means pumps of the same design family. When the flow coefficient, defined as CQ from these variables, is kept the same in two similar pumps, we get these relationships as a result. So we can relate one pump to another even with changing variables, just based on this. It's usually done through experimental data for one and then applied to the other, using these equations. Some special pump scaling laws with the same flow coefficient, and in this case, the same diameter, we get some relations with the rotational velocities and other variables. For two pumps, also with the same flow coefficient, and the same rotational velocity omega, we get relations between these variables in the diameter. If you notice, the diameter has a bigger influence than the rotational velocity in comparison. And it should be noted that viscous effects are ignored in these laws. So if you're operating a small pump, for example, it might not be as great of an idea to use these relationships. Now for specific speed, this is another way.
What are turbines? Turbines are devices that extract energy from a flowing fluid. There's two major types of turbines. There's impulse turbines and there's reaction turbines. For impulse turbines, the force on the blades is produced solely by turning the fluid, and then for reaction turbines, some of the fluid force is from fluid turning and some is a reaction to acceleration of the fluid relative to the vane. Degree of reaction is the ratio between the drop in static pressure across the moving blade over the drop in static pressure across the fixed nozzle plus the moving blade. For impulse turbines, the degree of reaction is equal to 0, and for reaction turbines, the degree of reaction is between 0.1 and 0.7. Generally speaking, impulse turbines are high head, low flow rate devices, and reaction turbines are low head, low flow rate devices. High flow rate, sorry. Impulse turbines. The most known of impulse turbines is the Pelton wheel. Unlike most other turbo machines, the Pelton wheel is neither axial nor radial flow, it's tangential flow. As water enters and exits the buckets, the magnitude of its relative velocity doesn't change, but its direction does, because the water will enter and then shoot out through the sides, as shown in the images. The change in direction causes a torque on the rotor, resulting in a power output from the turbines. The equations to solve for the torque and power of a Pelton wheel are shown below. From these equations, we can conclude three things. 1. The power is a function of beta. However, beta is usually equal to 165 degrees, resulting in a reduction in power since 1 minus the cosine of 165 degrees is equal to 1.966, compared to 1 minus the cosine of 180 degrees, which is equal to 2. Although the torque is maximum at U = 0, there is no power under this condition, thus both force and motion are needed to extract power. And the power output is at its maximum when U max power is equal to V1 divided by 2. Another type of impulse turbine is a multi-nozzle. Within a multi-nozzle, there's a series of jets that strike the blades, which alter the direction and magnitude of the absolute velocity, as with the Pelton wheel. Just as the Pelton wheel, the inlet and exit pressures are equal, and the relative velocity is unchanged. The fluid, which is usually air, pushes on the blade in the direction of the blade's motion, thus the fluid does work on the blades. This type of turbine is an axial flow device. Now we have reaction turbines. In this type of turbine, the work fluid completely fills the passageways through which it flows. At very low heads, the most efficient turbines are axial flow or propeller turbines, an example being the Kaplan turbine. For Kaplan turbines, both the inlet guide vanes and the turbine blades can be adjusted. This is convenient because if the flow rate or the head change, you can adjust it to get optimum output. Typically, radial flow or mixed flow hydraulic turbines are called Francis turbines. For these turbines, the rotor decreases the angular momentum of the fluid, causing a torque on the rotor which extracts energy from the fluid. Here we have some dimensionless equations and calculations for turbines. The dimensionless parameters of flow coefficient, head coefficient, and power coefficient are defined the same for pumps and turbines, though for turbine efficiency, it's the inverse of what the pump efficiency is, as shown below. Though not dimensionless, power-specific speed is calculated with angular velocity in RPM, shaft power in brake horsepower, and actual head available in feet. These are our references, textbook. Thank you.